I'm Joel and I'm from the Netherlands. In this video we'll discover why a parabola would be a circle in perspective. This is my first math explainer video, which I made for the 2025 edition of the Summer of Math Exposition. This video explores concepts of projectional geometry and conic sections. Some knowledge of conic sections helps, hence is not required for understanding. Projectional geometry will be built just from intuition. The most important goal is not to show you a nice proof of a very not trivial theorem. No, it's more about seeing a problem in different ways, and about showing how different ways of thinking can lead to a better understanding of a subject. True, a parabola really is a circle when viewed in perspective. But why? How would you prove something like this? When I first heard this statement somewhere, there was no proof with it. Since then, I've been trying to find an answer. The internet was of no help, and I had no background in projective geometry, so I had to figure out the whole proof by myself. I tried different approaches until I found two that succeeded in proving it. One was an algebraic proof, the other uses something I call PCE conic sections. I will discuss both approaches together with an approach that didn't work. The projection, which isn't needed for the algebraic proof, we discover after that. Then we'll move on to the second section, where we define the PCE cone and examine its sections. With that in mind, we find another proof, which brings us to the end of this video. If you are not comfortable with a bit of algebra, you can skip to that second part. However, the two proofs do support each other in understanding the statement. So I recommend watching both proofs. Enjoy! The parabola transforms a circle under a certain perspective. We firstly need to define that projection. That is, a function that gives us the blue coordinates in this grid, if we know the black ones. But how to define such a projection? An important property of such a perspective drawing is that there is a horizon, above which there are no points projected. In this image, that is this line over here. How high the horizon is projected can be varied. So we need to include a parameter we call p in the projection, which is a measure for how far the horizon is from the bottom line. What we then want is to find for each parabola a p for which the projection transforms it into a perfect circle. So, like this. Let's first name our coordinates. The coordinates of the half-real plane, that is the black grid, will be named A and B, where B has to be greater than or equal to 0. And the coordinates of the projection, the blue grid, we name W and V, where W is greater than or equal to 0 but less than P, because P is the height of the horizon, and the horizon is not included in the projection. A, B, V and W are all real numbers. We notice that, as W approaches P, it approaches the horizon, often called the line at infinity, which would be when W equals P. So what we now need is a function psi of A and B that depends on P, and gives us output the coordinates WV. Think rigorously. The black grid is a half-real plane we call H, which is the set of tuples A and B, where A and B are real numbers, and B is bigger than or equal to 0. The blue grid is a stroke with height P we call P sub P, where there's an extra condition, because W, the second coordinate, has to be also less than P. The projection we now need is thus a function from H to P sub P, which means that the input is from H and the output is in P sub P. 5 in the blue grid is mapped to 1, 2.5 in the black grid in this particular projection, where P is 5, because if you go 5 up in the blue grid, you end at the horizon. But how could we define a projection like that? If you look at a perspective drawing of a grid like this, you can remark that the horizontal lines stay horizontal and come closer to each other when you approach the horizon. You might try thinking that the ratio between the distance from a certain line to the other one beneath it and the one above it stays the same. Then the line b equals 1 is mapped to the line w equals s, where s is a certain start value. Carrying on, b equals 2 goes to w equals s plus s over q, b equals 3 goes to w equals s plus s over q plus s over q squared, and so on. So if that would be true, w would be the sum from k equals 0 to b of s over q to the k. If you work that out, you get w equals this fraction, which is not so nice to work with already. From that you could define v2, but we won't go into that. I did, and it led to very weird results, so no, it's not true. The distances don't decrease exponentially. Then how? How should we define it then? Let's bring the blue grid back in. Look at this drawing for a while. What kinds of insights could you have? Maybe you see what I mean when I do this. We should look 3D, which is actually not that surprising, since perspective is all about looking to something 2D from a third dimension, namely height. Imagine having a paper in front of you and drawing everything you see before you on the paper on the place where you see it. Like this. Here the green bluey square is the paper, and if you draw that red rectangle over there on the paper, you get something like this. You draw every line from the corner to A, and the dots you get by intersecting it with the paper are where those vertices land. And now you can draw the edges back in, and you get the projection of that rectangle. And you see, it doesn't look like a rectangle anymore. It now is an ordinary trapezium. So that leads us to the following better definition of the perspective projection. You can feel the half Oxy plane, where y is positive as the plane you are observing, the Oxz plane as the paper, and A as your eye. Then a point C on the half Oxy plane is projected onto the point where the line segment through A and C intersects with the Oxz plane. You can prove that lines stay straight under this projection, which helps drawing polygons like we did with a rectangle. Algebra to prove our theorem. We start with what we know. C equals A, B, 0, and A of sub P equals 0 minus P, P. But wait a second, why setting the height of E equal to the distance from the paper? We will see later why that comes in handy. But let's start by figuring first out the equation of the line L through C and A. With a bit of linear algebra, you know that this is the equation of that line. You can check for yourself that this is right. This is the parameterized equation of the line. To find the point of the projection, L needs to be intersected with the Oxy plane. We do that using the fact that I is 0 there, which lets us express t in terms of the other variables and constants. If you substitute that into the equations for the x and z coordinates, the two are expressed in a, b, and p. Simplifying these equalities, we obtain these coordinates, which are equal to the vw coordinates, so there we have our psi. The only step we need to take before we can start the proof is computing the inverse of psi. Why, you ask? Well, for the parabola we know b equals a squared times some constant. So we need to express a and b in terms of v, w, and p, which is exactly what the inverse of psi does. Try this yourself. Pause the video and find the inverse of psi. Done? I won't go through all the details, but you can follow the steps if you didn't find them out yourself or were just too lazy to try. Now this is the inverse we're looking for. Oh yeah, I promised you a justification for defining A like we did. Well, if you do that, psi has the nice property of letting the two coordinates converge to each other when p approaches infinity. This is very natural, because if the horizon is drawn very high, the coordinates should barely differ. What we want is to substitute the two parts of the inverse of psi into the equation of our parabola, and showing that that equation represents a circle for some choice of p. Since every parabola is of the form y equals ax squared, where the top is placed on the origin, we use that form. After some simplifying and applying square division, we get this, which is a circle when s equals p, s times p equals 1. P equals 1 over s is then how we find the p for each parabola. Remark that this circle does have one perforation, 0p, because w wasn't allowed to equal p. Wow! Now we have proven our theorem. But maybe you had another kind of insight before. A parabola and a circle. Where have I seen those two together before? Wait, they are both conic sections. Can we maybe prove our theorem using that? Let's recap conic sections. A conic section is any curve you can get by intersecting a plane with an infinite cone, which means it has infinite height. There are 4 of them: the parabola, hyperbola, ellipse and circle, depending on the plane's angle with the cone's axis. The axis is the vertical line here, which passes through all the midpoints of all circles on the cone. Then k less than 9, which is less than 90, is then the angle between the cone's axis and the lines on the cone's surface. So it has something to do with the slope of the cone surface. When the alpha equals 90 degrees exactly, then a circle is produced. If a is less than 90 but bigger than k, it becomes an ellipse. If it's exactly k, it's a parabola. And if it's less than k, then it's a hyperbola. Actually, if you want to obtain a hyperbola, you have to place another cone on the top of that cone to get the other branch. Now you get only one hyperbolic branch with one cone. With that in mind, is there a conic section to be found in our 3D model? Note that the projection of a curve L is the curve formed by the intersection of all lines AC with C and L on the paper. So all lines AC form a surface. Maybe that's a cone when L is a parabola? Let's see. Unfortunately not. No, we know that there exists a P for which the projection is a circle. And since the paper is not perpendicular to the axis of this cone, it shouldn't be a circle, it should be an ellipse, always. So, no, it's not typically a cone. It might not be a perfect cone, it looks a lot like it. Maybe we could stretch our cone a little bit, such that it does form a circle on the paper. A circle can be obtained by stretching an ellipse along the short axis. That does turn out to lead to a good result. So I named that specific cone-like surface a PSC cone. How could we continue? This is how a regular cone is transformed into a PSC cone. The blue plane is K perpendicular, which means it's perpendicular to one of the lines along the side of the cone. But if you stretch it like this, now the intersection forms an exact circle. We can now start investigating its properties. Which angles form which sections? Can you get the same sections as with a regular cone? It turns out that it's true by observing what happens when you stretch each of the regular conic sections, that the same sections are formed. There are no new sections, they're only stretched. So K less than 90 is still the angle between the cone's axis and the lines on the surface. And let's fill out this table again. For the regular cone, we know that if A equals 90 degrees, it's a circle, but a stretched circle is an ellipse. If K was bigger than K but less than 90 degrees, it was an ellipse. And now it's mostly still an ellipse, except for that special case, when A equals 90 degrees minus K. Why not 90 degrees plus K? Well, alpha is between a line and a plane, and that angle is always less than or equal to 90 degrees. So if we do 180 degrees minus that form, we get the minus K. The other two sections also become a stretched version of the same conic section. So, if our theorem is true, then this is a PCE cone for the right P. Before we prove our theorem again, we have to rephrase it in terms of PCE conic sections. We do this like this. For every parabola there exists a P such that the lines through A and the point C on the parabola forms a PCE cone. To prove that, we firstly have to prove this lemma, which states that every PCE cone with that point A as its stop through the circle B with the regular circle we saw on the Oxz-plane forms a parabola when intersected with the Oxy plane, and every parabola can be formed this way. Convince yourself why this helps to prove our theorem. Let's first prove this first part. It's the easiest. Try to convince yourself that's true again. This part is very trivial, but if we go on to the second, it is a bit more tricky. Using the first part, there's a parabola formed for each P, so in particular for P is 1. If you multiply P by a non-negative vector u, as a result the whole situation is multiplied by that vector. So too is the parabola, which lets us obtain any new parabola varying u. Conclusion, every parabola can be formed this way. From that lemma follows that every parabola can be formed by at least one P. We only have to extend this to exactly one P. That can be done using one step, namely to use that this function, f of u equals q over u in this domain, is injective, which means there's exactly one P for every parabola. That is why parabola sometimes becomes a circle. You have learned about different ways of attacking a problem and have met different types of problem solving. However, mathematicians wouldn't be satisfied by now, because what would happen to a hyperbolic branch with a b-axis as the line through the foci, which is also a conic section? Is there a special P in that case? Or what would happen to 3D objects by using the intersection of the paper and AC again? Or for programmers, how could you implement perspective in a computer program? For a video game, for example. Try thinking about this yourself for a while. The answer to the second question is in the description. With that said, I'm wrapping it up. Thanks for watching. Maybe see you next time.